of Alberta. It's my pleasure to introduce to you Dekang Lin. I've known Dekang for several years from conferences. He got his PhD from Alberta and his bachelor's at Tsinghua before that, with a university some of you know quite well. PhD in '92 and his bachelor's in '85. And he's also served as visiting professor at MIT and right here at UMass. So he'll be talking today on knowledge discovery from text, a talk that has two subparts, both of which look extremely interesting. In addition to this kind of unsupervised learning task, Dekang also works on question answering and information extraction, and of interest to some of you, minimalist and principle-based parsing. So parsing under linguistic formalisms that are actually used by linguists, and which tend to be rather hard to parse. So it's our great pleasure presenting Dekang Lin.
Thank you, Jason. I'm very glad to visit here. It's a big language and speech processing center in the whole world. So it's my great pleasure to visit here. Today I'm going to talk about unsupervised learning from text. And this is a kind of a high-level diagram of what we're attempting to do. Essentially, we want to take this text as input, text corpora as input, and then we want to use a learner to extract knowledge from this using unsupervised methods. So in this talk, I'll first talk about data preparation. There are things you can do with just straight text, but you can do much more if you first parse the text. And even if the parser is imperfect, it still can generate a lot better learning data for the learner. And then I'll talk about the sort of dependency data, and lots of the learning algorithm is based on this. And then I'll talk about two particular learning algorithms. One is for concept induction, another one is for generating paraphrasal expressions. And finally, I'll conclude by discussing future work. So the parser I use is called Minipar, and I've been developing this parser for many years. Minipar is based on the minimalist program, but it outputs dependency trees as results. So here's an example dependency tree. Like if you have a sentence, they had previously bought bighorn sheep from Comstock. Okay, what the parser outputs will have, like they is the subject of bought, and bighorn modify sheep, and Comstock modify bought via this preposition from, and so on. And evaluation with manually parsed corpus, this evaluation shows that the precision for Minipar is about 88%. And this is actually, the precision is more or less constant across different corpora, like be it kind of novels, scientific writing, and newspaper reportage, and so on. They're more or less the same. Okay? And the recall for these dependency relationships vary quite a bit depending on the genre of the text.
When you say precision, are you counting the label also, or just?
No, just counting, like for this word, does it, like here, previously modified bought, in a parse tree, like tree bank, does it also modify bought? Okay. Yeah. And Minipar is fairly efficient. It does about 500 words per second, and this is on kind of like a $1,000 machine. So using this parser to parse a lot of text, for example, like my kind of working corpus consists of a gigabyte of text. And then what I do is to extract the dependency relationships from the corpus. And here I'll first show you what's the what this data is like. For example, if you have a word like say spending. Okay. This is the parser output. So, for example, it shows this NN means noun modifying this modifying relationship. So consumer spending occurred 151 times, defense spending occurred 123 times, and so on. Okay, and these are the verbs which take spending as subject. Okay, so spending rise or spending increase. Okay, and if you click one of these words, then here you get the actual sentences in which the spending increase occurs. So in this sentence, it's kind of spending on durable and non-durable goods increased, and this one is kind of spending on aids for families with dependent children, and then kind of this is a positive, a favorite target for political right has increased, and so on. So here you see this is kind of the parser is working, so you can extract these kind of dependency relationships even though the words are kind of pretty far apart. Okay. All right. So this is the. Okay, let me. Yeah. So essentially, like for each word. From this database, you can retrieve a set of words in which this word was used. From this database, you can retrieve the context in which like this word appears. So in a web page I just showed you, like we see like there are so many ways, so many contexts where we use the word spending, and it should also have the grammatical relationship between this word and others. Okay. And using this data, we can extract we can compute the word similarity between words. And the similarity algorithm is based on this distributional hypothesis. I think this is maybe credit to Harris. And essentially what that says is that if words appear in similar contexts, then they tend to have similar meanings. And here's an example. Like if you have a word like duty and responsibility, okay, then here, this is a grammatical relationship like verb from. Essentially, duty and responsibility were used to modify these verbs via the preposition from. And the blue words here were used with responsibility. So you can absolve someone from duty, absolve someone from responsibility or back down from responsibility. Okay? And the green words were used with duty. So bans someone from duty or something like that. And the red words were used with both. So there's one occurrence of dismiss from duty and one occurrence of dismiss from responsibility. And or you can excuse from duty or excuse from responsibility and so on. So essentially, when these two words essentially, you can compute the similarity between these two words based on sort of the percentage of the red words among all the words in here. Okay, that's the sort of the simpler version of this. And the actual similarity formula is a little bit more sophisticated than this, because there are some common words in here, and that sort of means less than some like more rare words. So the similarity formula takes this, use information theory measure to take this into account. Okay. So from this, then you can compute, say, duty, and then these are the sort of the most similar words of duty, like responsibility, obligation, job, and so on and so forth. And then you say function, and then there's kind of task, and these are the similar words of task, of function. Now, this similarity work was actually done like several years ago, and it's published in Colin ACL 98. And in fact, there are many other previous work in a similar style. And my only sort of difference is, one is sort of this difference in similarity formula. Another one is like I use this dependency data instead of just kind of proximity between words. Okay, and even though like the result kind of looks good, like especially kind of when I first got the result, kind of look at these similar words, they're kind of quite exciting. For example, like for Beethoven, you can get Brahms, Mozart, and so on. But the thing is, like as you go down this list, things starting to deteriorate, and you get kind of chamber music. This is still kind of pretty reasonable, but then you get Shakespeare. Okay, like they're still sort of, well, like, but you can see some similarities, and you get Napoleon, and these are sort of essentially they are sort of dead famous people, right? But as you go down, like you get tough guy and the grandparent and so on. So it's very hard. Like by this time, you definitely don't want this to be kind of tough guy to be a similar one of Beethoven. It sounds like a joke. But the reason why it got here is kind of like you play Beethoven, but you also play tough guy, and play is sort of important for both words. So like, and the algorithm, like essentially how do we get rid of these things that we don't want? And obviously you can use threshold, but like where do you set the threshold? And it's like there's no uniform threshold you can set. So that's the problem that I want to address here. And what we do is I want to kind of create clusters which are kind of cleaner than this. So we don't have this kind of group of words which kind of deteriorates. The clustering algorithm uses the same data. In fact, it first it computes the word similarity. Okay, but the main challenge here is that as a clustering algorithm, like it has to deal with lots of elements. Like there are in a reasonable, like in its corpus, like if you set a threshold, like if I only looking at words which occur more than 50 times, you still get kind of tens of thousands of words. Okay, so let's say there are 40,000 words, and each word may have like over say 10,000 features. Okay, because like each context where this word occur will be a feature, and if you count the distinct features of like the union of all the words, that's even bigger. Like so, a lot of clustering algorithms just can't handle this. And in fact, like when you look at kind of clustering literature, and when they are talking about kind of clustering in high dimensional space, they're talking about kind of 100 dimension. Okay, and this is sort of like several magnitude bigger. So before I sort of describe the algorithm, I first kind of just show you what's the like the result of this clustering is like. Okay, so I'll first use like one of my words, and later on kind of you can use like yours. If you put in the word sun, and then this one retrieves the clusters where the word sun belongs to. Okay, so the first cluster, like this is a name generated automatically. Okay, like like every cluster has a kind of number, and then I pick several elements in the cluster to name this cluster. So this cluster contains kind of Intel, Apple computers, and some microsystems and so on. Like essentially, kind of these are lots of kind of companies, like Sun as a company. And the second cluster in here is like it contains like planet, Earth, Jupiter, Mars, and so on. Like, yeah, I think in fact all of the planets are here, right? Well, the third cluster is a cluster of newspapers, because Sun is a kind of very popular newspaper name, and so here you get some like a big, yeah, it's a fairly big cluster of newspapers. And And in fact, kind of like you can use this to classify the proper names. Like if you get a proper names like, yeah, like this San Diego Union, right? Like if just out of context, it may be hard to guess what it is. But like with clustering, like you can actually kind of group this cluster with something like Washington Post, which is and then it's a newspaper. And the sun is also kind of it's a kind of a light, like a sunlight, moonlight, and sunshine, and so on. So like here you get sun as light, and finally, kind of sun is kind of a weather phenomena, and so it groups like these. So as you can see here, like for example, if you take this, like if I use Beethoven, if I find kind of clusters Beethoven belongs to, and then like this list is a lot kind of cleaner than before. It also contains more kind of composers than the previous result, the previous list I showed you. Okay, and also like this the clusters kind of like, as in the example in Sun, like it also kind of automatically identify different meanings of a word, right? Using this unsupervised method. Essentially, it identifies that this word sun has these belongs to these several meanings. So, like if we have another word like base, okay, and the first one is kind of like it's batter, conseco, and runner. Okay, like these are sort of these are baseball players. So there got to be a sort of a baseball player named Base. Right? I think. And also like the second cluster is kind of guitar, piano, and so on, like this kind of musical instrument. And here like, again, like here, if you look at the musical instrument, it's also kind of a much cleaner kind of a cluster. It doesn't contain the kind of junk that you have with this similar word list. And this is sort of the fish meaning of this. Okay, like there's salmon and trout. Yeah, and there's yeah, I don't know what's this. I don't know. There's yeah, base. It maybe it's kind of a proper name. Who knows? Maybe it's some kind of proper name.
It's sponsors for European soccer league.
Yeah. Okay, there you go. Yeah, I often find like this class. For example, I get this list. I didn't know who they are. Like get a bunch of people, and then I sort of I use the kind of
on the basis of the other clusters, I'm willing to believe she does.
Yeah, I got a bunch of names, and then I found out like they are sort of Middle East hostages. Like there's Anderson and Terry White and so on. Okay, and also like if you click like if you click this, for each cluster there's actually a associated maybe I will click something like say tuna, this fish sense. Okay, like these are the contexts in which the words in this cluster were used frequently. Okay, so you can say like these fish, they are active, they are plentiful, they are abundant, they are delicious, they are fat. Well, haven't heard of that. And there's conjunctions, like when you have one kind of fish, it's often used in conjunction, like this fish and another fish and so on. So you can have kind of like fishing, like you can have like halibut fishing and like rockfish fishing. You can have kind of different kind of sandwich, like fish sandwich, tuna sandwich. And so these are the verbs. So you catch them, and you like them, you eat them, you land them. Yeah?
Yeah, manure fishing.
Okay. Well, I learned a lot of English by looking at this. You hook them. Okay. So, I don't know whether, these are sort of my poster words. Like, anyone wants to try some words?
Put your own name in.
Sorry?
Or put Fred Jelinek in. Or Jason. No, put Fred.
Put Jason.
No.
Jason, like you hear, these are actually mostly the sort of female first names, right? Like,
you're learning something about my inner nature. Or some other Jason.
Yeah, so there are a lot. These are a lot of names essentially. There's another one. There's another name cluster.
That's me.
Okay, so
Dekang, you can explain where did the tough guy go?
tough guy. Okay.
Meaning in Beethoven, why did we get tough guy? And what changed from the last one to this one?
Tough guy. I see. This is a kind of an R-rated list, right? Yeah.
What are the collocations for this cluster?
Collocations for this cluster. Okay. If you click on this, these are conjunctions. There's school, so there must be an idiot school or something like that. Yeah, you get these are these are the subject of these words. So you have it is slob, or he's an idiot, and so on. The verbs, you can have them, you get them. It's actually these are pretty generic kind of.
Act like, that's good.
Yeah. Or maybe look at what's the subject. What do these people do? Like they say, they happen, do, and so on. Yeah.
Yeah. No, my question was in the Beethoven cluster. Why was tough guy not in it? Although it has some.
Why? Because for tough guy and Beethoven, for each word they relatively have fewer features, okay, and because they share this play feature. I mean, even though play means different in this two contexts, but it's the same word, and we're not distinguish between different usages of the same word. So if you just have one word with Beethoven, it plays a very play is a very important. So you get sort of non-zero similarity. When you get more different composer put together, the composer features, there are more composer features. And also another thing is you can sort of set higher threshold when you have a cluster. That also plays a role.
So you're still setting some thresholds?
Yeah, I'm still setting threshold, but you can set higher. For example, for Beethoven, if you set threshold say 0.1, you don't get many composers. But if you get using a sort of a composer kind of a cluster, a composer have a feature vector, And then if you set a higher threshold, you still get a lot of composers. Yes, David?
What's the most relationship between wide context optimal relationships and dependency relationships in your similarity scores?
I'm only using dependency relationships. I'm not using the sort of the co-occurrence.
Couldn't you use sort of wide context topics to further filter?
I didn't. I could have, I guess, but I didn't. Yeah.
So what's the data source?
A newspaper and there's newspaper and some other thing like this sort of R-rated thing, like you don't see them that much in newspapers, like I guess. There's sort of essentially I put all the track data, like there's the track news text, so there are 3 gigabytes of it, and together with some novels like I got from somewhere else, like from ETS, and together it's about like 5 gigabytes of text, and then I throw out a lot of these other throw out dependency relationships that are not very frequent and so on. Otherwise, kind of like it's just too big. Like actually, when I'm creating this I create one of my intermediate file was like 3.5 gig, just one file, and when the file is over over 2 gig, like some of the Unix programs starts to break down because like some of them use the signed integer as the file size, and then and then sort of it starts to break down. So actually, I also did the same thing for the for Chinese, and in Chinese, like I didn't do parsing, but like I don't know like how many Chinese readers. Not too many, yeah. But like this is like without parsing. This is kind of this cluster is actually also pretty good. Like it's without kind of carefully looking at it, kind of you wouldn't say kind of this is kind of worse than the previous one actually. Like, so yeah.
So these clusters are based on collocations.
Collocations,
Short distance, long distance.
Very short distance, just kind of neighboring and distant words, or maybe skipping kind of one word. Like,
thanks.
Yeah. Okay.
You do word segmentation.
No, I don't. Like,
okay.
Yeah, like I don't like. I'm only sort of using hypotheses of words. I don't have to say this is a word, but if this is a dictionary, it's a word. Like the fact it's overlapping with another word doesn't matter. Like I'm using kind of overlapping words. Yeah.
Thanks.
And so the clustering algorithm kind of roughly goes like this. First, I construct small and tight clusters. Essentially, for each cluster, I need a feature vector. I need a centroid feature vector. Kind of like, for example, fish. Kind of you catch them, you like them, you eat them, and so on. Okay, like your fish sandwich and so on. I want to get this feature vector. And getting this feature vector, you don't have to get all the words that belongs to this. Kind of you need to get a subset of the words. Then you can get a very good feature vector for that. And so what I do is, like for each word, in one of the earlier kind of demos I showed, like for duty, I get a set of words similar to duty, the top similar words to duty, okay? And this is a good place for looking for clusters, okay? Like, because if you look, like, there are 40,000 words. Like if you look for clusters, even if you say kind of looking for small clusters, like combination of 10 words is huge, right? But if you say I'm looking at top 20 most similar words of duty and I'm looking for 10 word clusters, it's a lot manageable problem. And chances are like you do find similar words in that top 20, okay? So the actual similar, the clustering algorithm is a clique based algorithm. Essentially, kind of like you view this thing as a graph. Like if two words are similar enough, then there's a link between these. Like each word is a node. If they are similar enough, there's a link between these. And then you are looking for clicks in this graph.
So you have a hard threshold
Yeah.
on the graph. That's interesting. It's unlike most clustering algorithms people here have tried.
Right. Well, yeah, because here I'm just looking for small clusters. Then you get, well, here some example, you get clusters like these sort of airlines, kind of they are clustered together. Okay, and then you get kind of musician, performer, actor, and so on. Like these are, so you get these small clusters. And for each one, and then like if you average the, compute the average of the feature vector of these things, and then filter out some of the features which only appears in one element, okay? Then you get a feature vector for, you get a feature vector for each one of these small clusters. And the feature vector of clusters are just like the feature vector for words. Like it consists of the context in which like one of these words appears. And and finally, I generate some kind of heuristic ranking of kind of which cluster is good. Like if a cluster contains more elements, it's good. Okay, and then so you sort all the clusters, and then you take the first one. If next one is too similar to one of the previous ones, then you throw it out. Okay, so then you get a vector of. You get several vectors. This is about like 1,500 vectors for nouns in this feature space. Okay, and then the next algorithm is called Unicon, which uses the result of this as a sort of the first step, and then build like bigger, more complete clusters. And this result is kind of published in KDD this year, but actually kind of we've changed the algorithm by the paper was really sort of published. And so the result you've seen is we call it Unicon 2. Okay, essentially for each word you find which cluster it's most similar to. Okay, and so for example, like for word like bank, and then you find kind of which one of the 1,500 clusters the bank is most similar to. Okay, and then you remove the features, the sort of intersection between this cluster and the word. Essentially, you say now I know bank belongs to this. Okay, what else bank belongs to? So you remove the features of the overlapping features, and then redo this process again. So for word bank, kind of the most similar one is this kind of thrift saving loans and savings institution and so on. Okay, so the next one is kind of corporation, institution, and then it goes on like there's the next cluster like this National Westminster. This is kind of like a bunch of British bank, and the next cluster like this is a cluster of like U.S. banks. And the next cluster is sort of a bank of banks, like these sort of central banks, like Federal Reserve and Bank of Japan and so on. And then bank is a company, okay, and bank is also kind of a hardware store, like it's kind of like a location where kind of customer go to and so on. And finally, like bank is a sort of a geographical kind of entity, and because like in the newspaper or in the corpus, actually like this is like this sense is actually pretty rare. Okay, so if you look at the top similar words of bank, actually like none of these words appear in there, because like it's just so the features are so weak. But because by this time you removed a lot of features that belongs to this other sense of bank, so then this starts to show up. So, all right. So that's sort of the part one of the of the talk. The second one is about an algorithm called DIRT, which stands for discovery of discovery of inference rules from text. This name is kind of inspired by some, like, I think it's Dekang or something, like somebody, like they have a program called Termite. So we're just kind of following them to use these kind of gross names. Essentially, kind of what we want is we want to have this text as input, but we want to automatically learn these paraphrase expressions, like X wrote Y means kind of X is author of Y, and X solved Y means kind of X found a solution to Y, or their meanings are similar. Okay, the motivation for this is that in information retrieval and question answering, this query text mismatch is often very like a difficult problem. Like if you have a query like what does Peugeot manufacture, and then you have sentences like Peugeot is a French car maker, or Peugeot builds cars, or even Peugeot's car factory. Like these phrases or expressions doesn't contain manufacture, but it, like, for a human reader, you can nonetheless recognize like all of these expressions contain the answer for the query, right? And so we want to get this paraphrase relationship so that we can do the query matching more intelligently. And the intuition behind this algorithm is similar as the similar word algorithm. And essentially, we also use distributional hypotheses, but we use it in an extended sense. And here's an example. Okay, like suppose you have an expression called X finds solution to Y, and then you can go to this parsed corpus and then extract all the instances of this expression. Okay, like find all the instances of this, and then you find there's commission finds solution to strike, committee finds solution to civil war, and sheriff finds solution to dispute, and so on. Okay, and if you do the same thing for X solved Y, and you find a committee solved the problem, like somebody's cloud solved the crisis, or sheriff solved the murder, and so on. Okay, and then we're saying that if these two relations, if they tend to relate similar kind of domains, all right, like so for example, this X slot, there are like the red words also appear in here. Okay, so there are lots of common words, and here the blue words are the common words like between these two Y slots. And then we're saying, like, if they have this relation, if they tend to link the same thing, and then we hypothesize they are similar. Okay, like so essentially, like if you treat these words as the context of the relations, and then here we have two relations which appears in more or less kind of similar context, and then we're saying maybe their meanings are similar. So how do we do this is again we get this parse trees, and then we have an algorithm to extract all the paths from the parse trees. Okay, like so for example, like the first one is this is like they, like this subject goes to non-subject and then to this from modifier. Okay, that corresponds to X buys something from Y. Okay, and then there's a kind of subject verb object. That's another path in here. Okay, and so essentially we extract all the paths from this parsed text, and we have some kind of constraint, like the two ends of this path has to be nouns. Okay, because we expect these fillers to be entities, and so we sort of expect them to be nouns. And also there are some constraints, like normally the path doesn't go across clause boundary. Okay, that's another constraint. So we have several constraints like that, and then you can construct kind of similar data as the sort of dependency database. And so, for example, like X pulls body from Y. So this corresponds to a word, okay, and slot X kind of like a relation. And essentially you have these are the fillers of X. Okay? So you have diver pulls body from blah somewhere here, and the rescuer pulls body from like bus and coach and so on. And by the time we get this database, we kind of lost the information about like which instance map to what others, but like we do keep the sort of the we do know like these are the sort of the fillers of slot X, okay? And like the others, like we have their frequency and the mutual information between this filler and this expression, okay? And then essentially I'm just reusing the word similarity algorithm. I say like if this is a word, what's the top 20 most similar words to this, okay? So there's we have a similarity formula for the for computing the similarity between two different expressions, and this similarity formula is essentially identical to the word similarity formula. It's exactly the same, except like in the other one, like instead of a pass, here you have a word. Okay, so it's kind of just the same, and yeah, I'll skip this so that I'll have more time to answer questions. So here there are these are some of the sample output. So you can have like for X solve Y, okay, like if you give it an expression, and then these are the sort of the top 20, like the passive usually it turns up as the most similar one, not surprising at all. Okay, it's interesting to to do another kind of learning to generalize from this, right? Like because like if you look at manufacture and the solve and many other verbs, you find like this passive form always turn up the same. So there are more learning could be done after that. And there are also X resolves Y and X finds solution to Y. There's X tries to solve Y. Like some of these are not kind of really paraphrases, but they are kind of related expression.
So why is there so much less noise here than when you used Beethoven?
Because this is top 20, like there's...
Sure, but all top 20 look good.
Yeah.
Towards the top 20 for Beethoven didn't, and I can't imagine these phrases are more frequent than...
Well, Beethoven, yeah, well, the Beethoven, the example actually, it's not, it's a smaller corpus. It's maybe, it may be kind of like a half gig kind of corpus. It is a smaller corpus, and it's also sort of the older result because I was just kind of reusing my old slides. Yes.
How do you? So 2 slides ago, you were presenting the paths that you had extracted. Oh, sorry, one more. 3 slides ago. So on this slide, you were presenting some of the paths that you extracted. You extracted sheep. X sheep is bought from Y.
Yeah.
How do you actually resolve that? Create that passive from the parse?
Not from. I don't create from here. Like I just record this as is. Like this is bought. This is passive. But some other sentence you have kind of X buys Y.
Okay, but
or X buys from Y.
This sentence isn't passive. So you're creating that.
Oh, I'm sorry. Okay. All right. This is my English paraphrase of this sort of cryptic form.
Okay.
So what really recorded is this.
Okay.
But I'm sort of paraphrasing it to make it a little bit easier to understand what's this, what this is about.
So presumably that has to, unify or match if the passive was written down. So if you had a passive sentence, that would generate that path as well.
Yes. Yeah. If you have a passive sentence, it would just generate the, if you have like. yeah, if you have a sentence like Bighorn sheep was bought by Acme, okay, and then I will generate a relationship kind of X like by
But you generate both the passive and the active, even if it was in the passive form.
No, I only generate the passive form. For a passive sentence, I only generate a pass which include this passive form. There's no
There's no morphology. He gets the
Yeah.
by clustering later.
But from the active sentence, you're generating the passive form and the active.
No. Like this is paraphrase. Okay, this is paraphrase. Like this is still using the word as a.
Why isn't that bought? I guess is the question. I mean,
Why is that-
these paths are supposed to be extracted from the dependency
Well,
parts on the top
okay.
of the slide. Right?
This one, it corresponds to this path. It goes from bighorn to sheep to bought, then to from Comstock. It corresponds
Yes,
to this path.
But you seem to be doing morphology to turn bought into buy.
Oh yeah, like parser does this, but
Thank you.
yeah, like there's the parser has sort of a past tense and so on. Like yeah.
But it doesn't swap the arguments and passives.
No, it doesn't correlate the kind of X by the passive form. It doesn't correlate the passive form and the active form.
Good. I think that clarifies it.
All right. So another example like this would involve just nouns like X is role in Y, and you get kind of involvement. Or you get kind of X denies involvement in Y. It's not kind of paraphrase, but it's kind of often it's true. Oh, X is conviction in Y. It's like you get like this sort of there's implication and so on, right? Like conviction. But there's X witnessed Y. It kind of starts to be bad. And this is kind of causes. Like X causes Y, kind of you get Y is caused by X. Again, kind of this passive form, like you come up with as the top one. And you have kind of X leads to Y. And one thing is kind of because you can, like causal relation is sort of between events. Essentially, the two rows they come from the same domain. Okay, so then the passive kind of active goes this way, passive goes the other way, and then the program doesn't have a way of distinguishing between these two. So that's kind of one problem.
So reversible passives, you're going to have to learn a rule at some.
Yeah.
You're going to actually have to learn the morphology at some later stage.
Yeah.
Same with KISS or something.
So. Oh yeah. Okay. Actually, yeah. Here's I mentioned this. There's there are some limitations to this. One is like other distributional based learning, it's very hard to distinguish like synonym and antonym based on distribution. Like for example, actually like if you look at similar words, the most similar word to black is white, and when I kind of show this to one of my colleagues, kind of like he was horrified, like. So there's that problem. So in like when you have X solve Y, actually like if you like top 20 is still okay. Like if you go down a little bit further, like X worsens Y is also one of the sort of top ones, and it certainly doesn't mean solve Y. Then there's this sort of indistinguishable kind of role between these two. This problem kind of mentioned about cause. As for like future work, I want to look at kind of combine these two things, because like in this paraphrase, I just use this variable X and Y, okay? But it sounds more reasonable if kind of you replace the X and Y with more semantically contained contain the restricted classes. For example, like when you say have company manufactured artifact, it kind of similar to kind of company's artifact factory. But you have if you have like company's location factory, like Peugeot's, like Toyota's Kentucky factory. It doesn't mean kind of Toyota manufacture Kentucky. It means kind of some like manufacturer kind of in or at this location. And so I want to kind of have this used in like more constrained kind of patterns. And also like eventually kind of the ultimate justification for this is to kind of make a difference in something like question answering. And we did try this in track 10, and the result is not as good as we wished. Part of the reason is like for this particular track, there are lots of questions doesn't involve like relations. There are lots of definition questions. Kind of what is X? Like what is aardvark? And then kind of like there's very little kind of thing kind of automatically generate paraphrase you can use. And there are some like who invented something, okay? And then we essentially kind of what we did was we read the questions and then read the track questions by this program and then kind of parse it and then pick out kind of all these relations that and then we paraphrase them and then stick this in the like automatically kind of put in the lexicon and then the lexicon is then used by the system. Okay, so there's a two-pass processing of the questions, but it's because there's no human intervention, so it's still kind of within the rules thing. And we, for example, like when you have this event, like we get kind of like X patent Y, and which sounds like a very good paraphrase, but like whether this good paraphrase will actually make a difference for the question, it's another matter. Like we also get something like inventor of something and so on. But so, anyways, it's still kind of preliminary, and I mean, like it's hard to actually apply these things. And finally, it's kind of like in the old style AI, you kind of will knowledge engineer a lot of these things kind of we're talking about, like building a semantic network containing these concepts and these relationships, and like here kind of we're getting closer to kind of construct these kind of semantic network automatically. Right. That's all my slides.
I wonder if this data could be used to construct more complicated relationships than just similarity. Like the data for duty and responsibility seem to be that all the places, many of the places where you can use responsibility, you can use duty, but not the other way around. It's kind of like duty is a specialized kind of responsibility.
Okay.
That is a relationship.
Yeah, that's probably true. That's a very good suggestion, and I haven't looked at that. Like the similarity formula I use is symmetrical. Like, but like in the a lot of people argue kind of that there's this similar to relationship which is not symmetrical. Like you can say kind of like this lecture is like a sleeping pill, right? But you don't say kind of like sleeping pill is like his lecture, like you don't say it the other way around. So I haven't really looked at that. I'm only looking at this kind of symmetrical relation. Yes.
So to what degree? What degree do you think these kind of local paraphrases? How many of them? Is it a small set? Is it a big set? I mean, do there exist? Could you keep on finding them for an infinite amount of time, or is it, after you find, if you really could get the top 20, that's all you need, and then
Yeah.
You know, the rest is just, you know, you don't have to look any further.
Okay. This is kind of the paraphrase kind of go back to Beethoven example. Like I get a list, but I don't know where to set the threshold. So I could have kind of applied the same trick as before, and then kind of creating clusters of these, and hopefully kind of that's better.
Oh, no, but I mean, but do you think that? I mean, is this for any particular phrase? Are there, you know, hundreds of ways of saying it, thousands of ways, or like tens of ways? Just, I mean, like company manufacturers artifact. How many paraphrases are there existing to be discovered? If you could find all of them. I
think when I look at the list, like if I like top 40, mostly they are pretty good. Like there's maybe kind of less than 1/5 they are not as good, and then like even among like 50, like between 40 and 50, there are still a few good ones and so on. Like I don't know whether this answers your question. Like
yeah, I mean, I just like if you look for, are there 100 for you to find? Like, are there 100 which exist, or are there only 40 which exist?
So far, I haven't really run this on a big scale. Like for right now, like if you get for any given expression, then I can retrieve its top, the most similar one. And this, at the moment, it takes 5 minutes to do just one expression. And if you want to do this for kind of like for doing like similar words, like where kind of, let's say you get kind of 200,000 these binary relations, and if you want to do all of them, right now like it's just taking too long. So I haven't done that, and so I only look at like these few examples I've showed you, and for these I would say like around like 50 they are kind of good, and beyond that like they're not so good.
Yeah, I guess what I'm asking is what is the recall, and then what is the upper limit? But if you don't know that, I don't know. It's hard to know recall. Like for example, like this manufacturer like Axis Y factory, like you can't, like in this case you can't have humans to generate something as recall. Like
what you could do is something like question answering task, where you say you know that the answer is somewhere in the document.
Oh, okay.
Does this actually match the pattern in which it's in the document? So this is actually a weighted recall measure, right?
Okay.
It's saying, does this in fact find the ones which are most likely to express answers to this question? Yes. I had the same question. These are at lunch you promised better clusters than have heretofore been seen, and these are absolutely the most precise clusters, especially the most precise large clusters that I've ever seen by a long shot. Yes. But it would be interesting to know how good the coverage is for actual tasks where you might want to be able to get these relationships or synonyms or whatever.
Yeah.
IR, question answer, or whatever. But I'm sure you're going to continue doing this work all day soon.
Yes.
I had a question about the clustering. The way you went about it, you initially made these tight clusters and then you started putting the other words into clusters.
Right.
I'm wondering if the order in which the words go in tells you something about the hierarchy. It's a little bit like Paul's question. So suppose a cluster initially contained father and mother was not close to that cluster for a while, and then maybe then you put in parent into that cluster, and after that it was found that mother is close to it. That maybe tells you that father and mother are sort of specialized kinds of parents. Is there any such? First of all, do you have any insight on this? Does this actually happen, or?
It's not added one by one.
Okay.
Because when you get a small cluster, like father and mother, they probably grouped in a small cluster to begin with.
Okay. No. So let's just play along and think of some other words which were not initially grouped together.
If I go back to a slide.
I guess my more basic question is there any hope of discovering hierarchy in this procedure? Because the way you described the clustering, it appeared to be flat. As in the end, you got groups. And a word could, of course, belong to multiple clusters, but there was no notion of these three clusters, if you were to reduce the number of clusters, would be put together in one big cluster on top?
Actually, yeah. That was like I have this is kind of Unicon 2. The Unicon algorithm is actually exactly what you described. It kind of start with these little clusters, and each cluster has a feature vector, and then I sort of recursively use this clique-based clustering algorithm on the cluster of clusters, and then I merge some of these clusters, and then grow them kind of bigger. And but I find that kind of this result is better, like for some reason.
The flat one.
Yeah, the flat one is better. And but you can, like, for each one of these clusters, you don't just get the members, you also get a feature vector. So for between, like, there are 1,500 clusters, and I actually have a similarity matrix among these 1,500 clusters. So when you see, like, in the say bank, right? You get kind of a cluster of British banks, a cluster of American banks, and the similarity between those two clusters got to be much bigger than sort of similarity between those clusters and sort of hillside and so on, like the other cluster. So there is you can get the similarity between clusters, like if you want to. Yes.
I was just thinking that your polarity problem, where you have x solves y and x worsens y coming together, might not be unsolvable. There have been a number of papers on trying to detect polarity. One of the common techniques that's used is conjunction. So you see black and white, or black or white, black versus white. Does it solve the problem, or does it worsen it? And various things that might tell you that in fact they're in distinct classes.
I see. Okay.
And maybe that's enough to help you start to partition the space, although what you're looking for is something like a bipartite graph, and it may not be complete enough to do it. Nonetheless, I never really saw very much application for that work, because there was never anything real to apply it to. But now that you have these clusters that can't distinguish them, maybe those methods can be resurrected and applied here.
Yeah, maybe. Yeah, that's a good suggestion. Yeah.
Who's the reference?
I'm trying to remember. I think Sharon Caraballo had a paper about that a few years ago. Not positive. I've got a couple of other names that are bubbling to the surface, but
yeah,
I'm
I
not sure
think Vasilia, like this guy at Columbia.
Vasilius Vassiliou.
Yes, actually, he did do some more of that.
Sorry?
Yes, I think he did.
Yeah.
Yeah.
Yes.
I would suppose that the time complexity of the clustering algorithm blows up most quickly when you clip size that you choose to use, or when the purpose you're acting on.
The
Which?
complexity, the most time, sort of the complexity part is the clique. I mean, clique clustering, like finding maximum clique is an NP complete problem. But if you reduce the input size to reasonable, like 20, okay, like then you can get kind of like fairly efficient clustering algorithm. And if it's efficient, like it doesn't take long to do say 50,000 words, like one by one. Okay, so the key thing is, like, as long as kind of you reduce the size of the potential cliques that you're looking for, you can find this efficient algorithms.
So what's the kind of behavior, if you look at the trade-off behavior in the reductions in accuracy versus time speed up by increasing the size?
I haven't, like, the hardest thing I find in sort of this work is evaluation, like how, like it's good kind of to show you guys here and so on, but when you write papers, you don't have a chance to do this, right? And so kind of to come up with an evaluation method, it's extremely hard. Like, but this goes to any kind of unsupervised learning, and so I'm looking for good suggestions.
You can use language modeling, or information theory performance as test beds.
for this. Yeah.
Are there any of those techniques?
Um,
Problems?
Not yet. This is kind of fairly recent. Like both of these are sort of the work we did this year essentially. Like, yeah. Yeah.
So I have some inkling of the answer to this question, but you're going to be able to give a much better answer. Can you talk about sparse data? So if you have words that don't appear very often, what happens to them? And are some of the features of your algorithm, like finding small clusters quickly, designed to combat sparse data?
The fact you get a feature vector for this, when you get a feature vector for one of the small clusters, okay, the features are sort of more related to these words, to the cluster. So if you have another word which is kind of relatively like infrequent, okay, then infrequent will tend to have smaller feature vectors, right? And if you're just comparing this with words, and the other words have a lot of feature vectors, okay, so just by like then their similarity couldn't be high, like couldn't be very high. Okay, like what would be a good example? Yeah, a example is like what? Okay, say you have you have some kind of more obscure kind of airline, okay, and it doesn't have many features, but when you compare this with something like kind of say Northwest, which occurs a lot more frequently, and but because Northwest feature vector is huge, and this one is kind of small, like then like for example WestJet. Okay, I'll just use kind of this is actual airline in Western Canada, like WestJet. Like probably nobody heard of it. Anybody? Nobody. See, like well, it has very infrequent usage, right? Sure. And if you look at Northwest, and sort of Northwest kind of has many features, and some of them kind of used as airline, and some are not. Like you kind of talking about Northwest stock and so on. Like there are. It's not sort of particular to airline, but if you have like merged these airline company together, the features are really characteristic of airline, like kind of jet, pilot, and cancel, and so on. They sort of stand out more. And then when sort of WestJet has pilot and cancel flight and so on, like then this feature becomes more significant. So when you compare the end result is the similarity between WestJet and the feature vector for this cluster may be higher than the similarity between WestJet and any one of these words. So that's kind of how, like if you just look at the top similar words of these guys, you don't find WestJet. But
sure. So suppose when you first see WestJet, suppose it's only occurred once. WestJet serves Western Canada or something like that.
Right.
And so you have to find neighbors of it. What's going to happen? You're going to look for, this is what I'm guessing, you find all the things that have occurred as the subject observes. And then you cluster them, and either there are no such clusters or there are clusters that end up, that you find clicks, I'm sorry. Either there are no such clicks or there are clicks that actually have to do with serving food in a red, so you're going to get words like waiter. But that's okay because those are used as the seeds for adding things. So maybe WestJet gets added to them, but it doesn't corrupt anything.
Yeah.
Is that right? That only the ones that...
Okay, let me see this.
The seeds that you start with are quite reliable and don't cover that many of the words. But you're very sure of them, and then you just add everything to them one by one. I'm just trying to get a handle on the sparseness issue.
Yeah, if you just have one occurrence, I don't think right now I can do much. Like, Well, I haven't done much. I wouldn't say I cannot, but like I haven't done much to look at like if you just have one occurrence, what can you, like if you say WestJet serve Western Canada, like it could be like it could be airline, but it could also be serve a gas like.
Sure, you might put it in the wrong cluster. The question is whether it affects anything else that happens in that cluster.
But
I'm guessing not.
Are you throwing out words which don't occur below a certain threshold?
Yes.
Oh,
Yeah.
what's the threshold?
Okay.
What's the threshold? It's probably around 50.
Around 50.
50, 50.
50.
5, okay. Okay. So it still may occur with any given word. I mean, the collocations may be rare, but there are a lot of collocations.
Yeah.
Okay, well that makes a lot of difference actually. It is true that, I mean, I just want to ask the technical question again. If you put up the slide where you explain Unicom 2. So when you say repeat the above.
Repeat these two steps.
Yeah, in Unicom 2.
Yes.
Do you update the centroids after you add things to the cluster? Or do you just leave the old centroid for the cluster?
Oh, I use the old centroid.
That's my question, thanks. So things that you added that you weren't sure about aren't going to corrupt the centroid?
No.
All right.
Okay, thank you.
Thank you.